Good morning, everyone. Welcome to the second day of AI and Science, and also the first session of AI and climate modeling. I'm Jane Bay. I'm the chair of this session, and it's my honor to introduce our first speaker of today, Laure Zanna. She's the Joseph B. Keller and Herbert B. Keller Professor of Applied Mathematics in the Department of Mathematics at the Courant Institute at NYU. She leads M-Square Alliance, which is an international collaboration to improve climate simulations using scientific machine learning. She received the Nicholas P. Fofanoff Award from the American Meteorological Society in 2020 and was the WHOI Geophysical Fluid Dynamics Principal Lecturer in 2022. Her research focuses on studying the role of the ocean in climate on local and global scales through theory, numerical simulations, and machine learning. So please.
All right, good morning, everyone. Hope you had a great day yesterday and evening. I definitely did. So I'm looking forward to today as well. And so thanks for showing up at 8:30 in the morning. So it's really exciting to be here. So I've learned a lot yesterday, so I'm hoping to kind of give you a little bit of a background on the way we are thinking about using and developing AI for ocean and climate modeling. So let's see, there we go. So I'm going to talk about a problem that you heard a little bit yesterday, kind of, the flavor of, multi-scale problems, trying to actually build AI emulators over very long time scales so we could actually accelerate simulations overall, but, also maybe understand something about the physics of fluids. So like everything else, I'm always the lucky one who gets to present what M² Line has been up to. But it's actually a collection of pretty amazing scientists. So we are domain scientists, climate model developer, machine learning experts, all working together across multiple institutions in the US and France. And we've been, very grateful from the support from Schmidt Sciences over the last few years to really kind of push the boundaries of using and developing AI to accelerate climate modeling overall. So I'm going to touch on a couple of, grand challenges, I would say. But first, let me kind of give you a little bit of a background of, ocean and climate overall, right? So the way we use models is to kind of solve the laws of physics. So what you see here, let me see, that works, perfect. So what you see here usually is basically the grid of a climate model. So we'll actually take the laws of physics, chop them up into pieces, and solve, at every single grid box, the equations of motion, both the fluids and the thermodynamics for the atmosphere, the ocean, and here is a little simulation from the GFDL lab in Princeton showing a relatively high resolution simulation. We're looking at sea surface temperature on an horizontal grid of about 1/12 of a degree. So about, 10 kilometers horizontally roughly. So those are really, I would say kind of state-of-the-art type simulations. But of course, there's a lot happening below 10 kilometers or below 25 kilometers horizontally, which is the typical resolution of existing climate models. And that means you need to, solve all those processes like clouds and turbulence and mixing in the ocean and atmosphere that are usually not represented on the grid of climate models. But nonetheless, right, they're still solving the laws of physics, and they've been a pretty, important tool for us to understand and simulate climate. And the way we use them usually is to, again, because we trust them, right? Despite their uncertainty, they're still solving, equations that we understand. We can ask questions. What if, the amount of, CO2 or different emission scenario will change? What will happen to the temperature, global mean temperature of the planet? And you can play some scenario. Let's assume that, we continue emitting at a very high rate, or if we were to reduce emission. So what will happen in those cases? And that's the way we use climate model. They're there to generalize. So we can actually explore different climates. We can also ask what might have happened in the past, right? So then in paleo time, in the distant past, where we have very few measurements, so we can use climate models to actually understand what has happened in the past. And so again, you can actually use different amount of radiation or, different aerosol forcing, and then try to understand what might have happened in the distant past. So we really are using them as a tool to understand the climate system and ask questions about mechanisms. Now, one aspect in which AI has been useful, and you heard about it yesterday from Jen actually, is what we call subgrid modeling. As I mentioned, there is a lot of processes in climate simulation that unfortunately we don't have enough resolution to resolve. And so that means we need to come up with what we call parameterization or closures. So you could say a little bit of an ad hoc way to represent the effect of turbulence on the large scale. And it's been an important part of having more faithful and accurate simulation overall. And so AI has been useful in a sense that we can use high fidelity simulation, as Jen mentioned yesterday. So we do the same for the ocean and the atmosphere, learn a closure based on data using machine learning or AI, and actually plug that back into the climate model and be able to run at the same kind of coarse resolution, 25 kilometers or so, with a more accurate, you could say, because it's data-driven, so there is no assumption on what the turbulence is doing on the large scale, and hopefully, right, we have a better representation of turbulence on the large scale, and then we're hoping that it would reduce what we call biases or errors in the climate simulation. So one of the errors and biases that has been around in ocean models for many decades, I would say, and it doesn't matter which model you pick, it will be there. So it will be an error or bias in the North Atlantic. So usually you will end up with a Gulf Stream that is too warm and a North Atlantic that is a little too cold. And the reason for that is that the Gulf Stream actually transports warm water from the tropics to high latitude. And the current is actually not strong enough, and one of the reasons is because turbulence is not resolved. And the turbulence usually re-inject momentum and energy into the flow and kind of accelerate it. But when you don't have enough resolution and not enough turbulence for that transport, that means you end up not transporting enough heat from low to high latitude. So that's why you end up with an accumulation of heat along the US East Coast and a too cold error in the North Atlantic. So this is a zoom in. So we learn from data, a closure, again, high fidelity simulation. We use a neural network. I can tell you the recipe because the recipe is important on how to learn those type of closures and plug it back into that simulation. So it's a global state-of-the-art, again, simulation of ocean ice. And then this is what we ended up with. So this is the response after we put the parameterization. So to look at the error, you would need to sum up those two plots, but it's just to give you an idea. So where it was too warm, we ended up with a temperature response that will be negative. Where it was too cold, we have a positive response. So basically, it translates as we ended up with a turbulence closure that re-energized the transport of the Gulf Stream, accelerated it, and literally counter-effected this kind of original bias that we had. So if you sum those two things up, you would end up an error that is reduced by more than 50%. So we were pretty excited, right, that we were able to tackle one of the long-standing biases in ocean models, which is the Gulf Stream is too weak because of a lack of turbulence. And so we felt like this is wonderful. The problem is we call it the whack-a-mole problem. So we fixed one and we find two others. So it is, I'm not saying that, I think it's important to talk about what we do well and the challenges that remain, that we're still facing. And one of the reasons is there are so many processes that are unresolved in climate models that when you fixed one, you discover that there are others that you also need to be tackling. But I still see AI here and data-driven, closure a very important way to help improve simulations overall. So as I say, it is a lengthy process, so you have to be patient. And as a scientist, I have two sides. I'm very patient and very impatient. So we've also been focusing in parallel on another approach of using AI to accelerate simulation. And again, this is something you heard yesterday from Anima in terms of accelerating weather simulation. So here, I'm going to tell you about accelerating ocean simulations overall with a different set of challenge. So first, again, I'm going to go quickly because you've seen that yesterday again from Anima. So, numerical weather simulation have been around for a long time. We use them on our phone all the time, but AI has completely transformed that, right? So here's a simulation coming out of ECMWF, the European Center for, based in Europe, basically doing weather forecast. And here we're looking at the skill of their AI version compared to their numerical weather forecast. And so now those predictions from AI are actually on par, if not better, than the original model. Of course, they use reanalysis, which is a combination of data and numerical simulation, but it's been a clear revolution. And again, we heard about ForecastNet yesterday and many other models that have been kind of, popping up everywhere. So it has been really a game changer, I would say. But when it comes from ocean and climate, we have the same set of challenges that you heard about yesterday from Anima. Again, this kind of multi-scale approach, the need to actually build, large ensemble at a, cost that is relatively cheap, I would say, right? And then how do we define cheap, we can talk about. But we also have that challenge that when we talk about long rollout, we are truly talking about hundreds, if not thousands of years when you want to think about oceans and climate in general. So we want to build those emulators, ocean and climate, that are kind of long simulations, right? That could help accelerate spin-up of the ocean, that takes thousands of years to equilibrate in general. We want to be able to build them the same way we use climate models in general, right? We want them to generalize. I want to ask question, what if I were to change emission? What if I were to change radiation? So we need to be able to trust them, right? And over, again, very long rollouts that are hundreds of years. And again, we want to explore extreme events and, a bunch of other methods. And so the way we go about this is we're going to take data coming out of simulations, right? So I still want to make a prediction from time t to time t plus delta t, given some forcing, but I'm going to replace the PDE solver, so the partial differential equation solver, with a big neural network. Now, like everything else, there are challenges, and we didn't solve all of them, right? So one of the challenges, again, I just talked about it, generalization. The second one is the span of spatial temporal scale that we're talking about is really humongous. So in the ocean, we're talking about scale of meters and seconds, all the way to thousands of years and thousands of kilometers. So you really need to span a very large spatial temporal range, and you want that to be as accurate as you could. Okay, so one example of an emulator that we built, taking data from, again, the GFDL model, here run at 1/4 of a degree. And so the model actually solves sea surface height, horizontal velocity, temperature, salinity in the ocean, with, again, a traditional PDE solver. Again, very accurate. I will, skip the detail of how the simulation works. It's forced by the atmosphere, so reanalysis atmosphere, so observe over the last 60 years, and again, predict the same fields after, a certain delta t. So we're going to use data coming out of that numerical simulation to build our emulator, meaning we're going to replace the PDE solver to actually do this prediction from time t to time t plus delta t, given the data. All right, so this is just what I said, and now we're going to replace, again, with a neural network, a big UNet. Won't give you too much detail, but let me give you a few pieces of detail. So first of all, the amount of data is pretty vast, to say the least, right? We're going to take, so the numerical simulator basically, give us data on, 70-something vertical level at 1/4 of a degree resolution at every single time step. So it's pretty difficult to ingest in memory on the GPUs, right? So what we do is we actually coarse grain the data to 1 degree, 5 days averages, 19 vertical levels, and we do that conservatively, again, because we want to be conservative globally. We don't want to have leakage of heat or salt and so on, which are critical for climate. But how we do that is important, and I'll come back to it in a bit. Then the architecture, we took a UNet here. Again, it has a lot of nice properties of kind of being able to encode multiple scales at once. 135 million parameters, right? So for climate scientists, they really freak out when we say something like this. But if we were looking at the number of grid blocks that we have in a model, then it's not that dramatic overall. But it's still a relatively large network. Now, the other thing that we do, sorry, let me go back, that I didn't mention, we actually do what we call 2-in, 2-out. Basically, we use 2 time steps, so the current one and the previous one, to predict 2 time steps in the future. So you can think about it as kind of predicting a rate of change of temperature, a rate of change of salinity, and a rate of change of momentum, which is pretty much how models work in general. You add a force, and this is what you predict. Okay, so then the data that we take is actually basically kind of reproducing, if you want, the historical period of the ocean. So that means there is some kind of weak warming overall. So we're going to take a chunk here to train and validate the data. And we're going to test on the last 8 years of the simulation where the ocean warming is actually a little bit stronger than before. But if you look at the scale here, it's still kind of a weak warming compared to, say, the seasonal cycle or things like El Nino, which is kind of a large mode of variability overall. Okay, just kind of recap. Mathematically, it looks something like this. We're going to predict the state of the ocean at 2 time steps, given as input the previous 2 time step, and the atmospheric forcing. And we're going to autoregressively, train and roll this out. So again, a little schematic here. The loss function is actually pretty trivial. So there is no additional constraint in the loss. It is a simple mean square error loss over the variables that I mentioned. But we do have 4 recurring time steps. Since the data is average over 5 days, 4 recurring time steps mean we basically have information about 20 days, right? And now we're going to try to roll this out for years overall. Okay, so, I'm an oceanographer. I would say if somebody showed me those 2 pictures, I couldn't tell you which one is the autoregressive emulator versus which one is the original data. So this is the ground truth of temperature as a function of depth and latitude. This is the original numerical simulator. This is Samudra, our ocean emulators, again, depth versus latitude. So you can see kind of the ball of what we call the thermocline, which is relatively warm, and then the ocean gets colder. We do a pretty good job at capturing the mean ocean simulations overall. Here is another picture of depth versus longitude in the tropical Pacific. This is basically a signature of El Nino. We're looking at temperature anomalies that propagate along the equatorial region, so it's basically wave propagating back and forth. And again, up here is Samudra, our ocean emulators. Down here is the truth. Again, we capture a depth, the right depth structure, if you want, and the right propagations of wave, again, given an atmospheric forcing. So mean and variability are relatively well captured. Now, let's zoom in a little bit more carefully. Now we're looking at the truth over here, still Samudra on the right, and we're looking at the variability of sea surface height. So you can think about the ups and downs, of the surface of the ocean. Again, some of it is forced by the wind, some of it is the internal variability of the ocean. Now, what you can see is the variability is a little bit more muted, right, in Samudra. It's a little more quiet. One of the reasons is because we did coarse grain the data, so that has an impact, but also this effect of smoothing that Anima referred to yesterday. There's a little bit of blurring, and also one of the reasons is we learn over a relatively short time scale compared to those kind of multi-year emulation that we're talking about here. So that remains a frontier when we talk about very long integration. Now, of course, we don't have a real, observational data set to compare very long integration, but what we can do is we can repeat the surface forcing and run Samudra for hundreds of years. And now the good news is we're looking at global mean temperature in 2 versions of Samudra. I'll come back to it in a second. It runs stably for hundreds of years. So you can actually use it as a full ocean emulators now in something that can run, again, stably under repeat forcing. Computational cost. So here I'm talking about it in terms of, we measure it as time to solution, right? So it's not replacing a PDE solver. I want to make that clear. We're just emulating the solution of a PDE solver. But nonetheless, what, as you could say as a user, what you care about is really the time to solution, so you can actually do something with the data and the emulation. So the original OM4 runs 12 simulated years per day on almost 5,000 CPU core. Samudra run 4,000 simulated years per day on one A100, right? So you can see the difference. So anyone now can go over here, grab the weights, and run an ocean emulation on their laptop. So this is kind of cool because we get a lot of people now being able to really kind of access ocean model without being an ocean modeler and being able to actually learn something about the ocean. Okay, Chris will talk about Samudrace, which is a coupling between our ocean emulator Samudra and AI2 atmospheric emulator. So really kind of pushing the frontier of a full Earth system, emulation that also can run stably overall. So I'm leaving that to Chris. So I have, I think, about 5 minutes left, right? Is that correct? Yeah, great. So I want to tell you a little bit more of the challenges. I have 10 minutes, okay. Right, so I want to tell you a little bit more about the challenges because I think, in this room, what's exciting is we all have a set of challenges and we can learn from each other. So I want to tell you where we're still struggling a little bit. So one of them is, again, this interaction between fast and slow time scale, right? So over here, again, we're looking at global mean temperature as a function of time. The black line is the original model data. So, and the 2 versions of Samudra in pinkish and green. So why do we have 2 of them? So the original one was, as I mentioned, considering velocity, temperature, salinity, and sea surface height. The velocity has a very fine scale structure, while temperature and salinity have much larger scale structure. And when we actually use our loss function, they both contribute equally. And that means that the fast scale velocity have imprinted on the large scale temperature itself. So if I give you a map of temperature, it'll look a little bit like velocity, and it shouldn't, right? And so this is something that we've seen across many applications, not just the ocean, by the way, and something that we've struggled with. So what we've done, obviously, is to basically remove the velocities, because actually geophysical fluid dynamics tells us we can actually infer velocity from the gradient of temperature. So that helped us. And that's why we ended up with this kind of pinkish emulator, which is a lot smoother than the green one that has the velocity. And basically, you can see it's a lot more ragged. So the temperature fluctuates a lot more than the original data or the thermodynamics emulator. So that's been one fix, but it's not a great fix, obviously. The next one that we've done, and so now we're working with Open Athena, which is a nonprofit with absolutely phenomenal research software engineers. And so we've been developing kind of new training with them. Some of them is, of course, a wider network rather than a deeper one. And again, this is something we've seen in other applications. So that helped fix some of the problem. And the other one is a dynamic loss, where we actually have different contribution of variability from the different variables, so the fast one versus the fast one. And so that has been pretty important. Those are our new emulators. They also run now at higher resolution, actually, so we're pretty excited about this because we can fit more into memory. But now we don't have that problem of mixed scales anymore. And so that's one area where we still want to make sure that we can push the boundaries without those issues. Okay, the second issue, same plots, and as I told you, there is a little weak warming here, right, in the ocean. Some of it was in the training set, but we still can't capture it. And because that weak warming is minuscule compared to the large variability that you get over a few days. Now, if we try to actually have a soft constraint, or even a hard constraint, to try to make it globally conservative, it is very difficult to actually roll out the emulator over hundreds of years. We start accumulating error. So there's a little trade-off here between, again, those kind of very weak signals that we see underneath and the large-scale variability that you might care about on shorter time scale. So that remains a challenge when you think about very long rollouts. And again, this happens as well if we ask, what if experiment? If I had a much larger warming, would I see it? Yes, the emulator responds, but it responds a lot weaker than it's supposed to. So it gets that there is a warming, but it does not respond as strongly as it's supposed to based on conservation. So we're working on two new formulations, so one based on tendency, but this one, which we think has a little bit more legs, where we actually try to look locally to learn in a conservative form what's happening at the grid box level. And so that would make that conservation is locally true. And we're hoping that will help capture a very, very small trend because it has to be right at every single grid box. Okay, so now a final, I wouldn't say challenge, but a final experiment that we've been able to do. So a lot of the papers out there, in general, we all look at what might happen in the future if we increase warming and so on. So we try to look in the past. What if we take the same backbone of Samudra and then train it on a different data set, so a different climate model, and evaluate it against a climate of the past, okay? So the previous example were out of distribution, right? So now what we're gonna do is we're gonna do out of sample, but in distribution. So we're gonna train on what we call pre-industrial control, all right? So that will be this era, right? So we're looking at paleoproxy of temperature versus time. So this is us over here, and we're gonna test it in the mid-Holocene. So the global mean temperature in the mid-Holocene is roughly the same as today. But insolation was quite different, and the pattern of winds, for example, forcing the oceans are also quite different. But then if we look at the distribution of temperature, right, of those two simulations, they remain in distribution. So that's kind of to give you an idea. Still a very different climate overall, with different surface forcing pattern, different radiation, but still in distribution. Okay. I'll skip those details just to tell you, again, we used the backbone Samudra, but we did a few different things with the data because it's a different climate model and we want to run it for longer, but happy to talk about it. So we end up with a different seasonal cycle when you look at the mid-Holocene, again, because the amount of radiation is different. So in black is the original model in pre-industrial, and the other one is the change in the mid-Holocene. The dashed line is the emulator compared to the original model. So basically, if you compare the dashed with the black line, what you see is they kind of follow each other. And that's, again, exciting because it's a completely different forcing, both pattern and global insolation overall. So we can see that when we are in distribution, but at a sample, the emulator can still do a good job, even though we start struggling with kind of, out of distribution samples. And we get the right spatial structure, not just when you actually just look at an average. We get the right propagation of signals overall of temperatures as a function of time. So we thought that was kind of an exciting challenge. Okay, so now let me wrap up. So Samudra, it's a backbone for ocean emulation from climate model simulation, right? So we're trying to emulate the solution of a PDE solver. It's open source, as I mentioned, so any of you can now use it, both the code and the weights. So we've been now using it for a few models, as you saw. You're going to hear more, I guess, from Chris in a minute. We've been also using it as a backbone to emulate biogeochemistry in the ocean, which is even more complicated, I would say, than the dynamics. It's even much longer timescales. And now, again, as I say, it's coupled with ACE, so I'll let Chris talk about this on the applications. We've been expanding the capability of Samudra, again, as I say, with OpenAthena, but also with NVIDIA. So new backbones, trying to ingest multiple resolutions. Again, many new downstream application, and as I said, some locally conservative architecture to try to capture local trends. So happy to leave it here. So then about 5 minutes for question and happy to discuss further. Thank you very much. Hold on, I think there's a mic coming to you.
Sorry. Do I need to repeat? Okay. So 2 questions. The first is seems like you are directly model the evolution for 5 days or so. And the model does not have information of the longer time range, for example, a solar cycle of 11 years or so. And I'm very surprised to see the model rolling out for 10 years or 100 years, the results still manage to capture those long-term period. So how did they manage to do that?
Yeah, thanks. That's a great question. So indeed, right? So we are only learning, if you want, from 20 days, because it's 4 recursive time steps of 5 days. So it gives us 20 days. Now we are forcing it with the atmosphere, right? So the surface pattern comes from the atmosphere. So the ocean sees the atmospheric variability as we force it. So it sees some information about the solar cycle, if you want, but then it's able to reproduce actually the full depth overall.
The second question is more technical.
Sure.
So in your later discussion about relative out-of distribution and something, and you say that you want to read the information of temporal derivative or temperature field or something, and how did you use the information of the temporal derivative of those fields in the training?
Sorry, could you repeat that? I'm sorry.
The time derivative of temperatures.
Oh, how do I get the time derivatives?
Yeah.
Okay, so in the training or in general?
In the training.
In the training, yeah. So, the model output is going to be given either as a tendency, which is a time derivative, or as basically the field at a given time, right? And so what we do is we basically aggregate or average over a certain amount of time, take the difference. We try to do it, again, conservatively, so we don't have a lot of leakage. And that gives us the time tendency.
But I understand you are doing a front-end inference with the time period of 5 days.
So yeah, but we do that directly within the model itself.
Oh.
So then we don't have any issues with a simple finite difference.
Okay, thanks.
Yeah, good question.
Really interesting stuff, Laure. I was curious, even if the emulator is struggling to kind of unroll into unseen climates on its own, do you think that you can use it to generate large ensembles if you use a physical model to unroll into a 4K climate, for example, and then use it over just shorter timescales to generate the right distribution? Have you tried anything about that?
Yeah, so that's a great point. So we see them really as complementary, right? So here I only talked about the emulator and the fact that, hopefully we'll be able to solve a lot of those problems. But the way we see them is really in tandem, exactly this way, right? If I can use something that is conservative to actually couple it with the emulators that are a lot faster, where I can do ensemble over a short time scale, this is really kind of the way we're thinking about it. The other one is to accelerate the spin up of the ocean. So then I get there as fast as I can, and then pick up with the physical model to actually get the trends. Yeah.
I think there was one last question.
Oh, I'm just curious, why do you need 2 time steps to train the? I'm just curious, why do you need 2 time steps to train the emulator?
So it was more stable, but now we moved with ACE to a 1 in, 1 out, and in the coupler, we don't seem to have the same issue. So there are still some interesting questions there that are, puzzling us.
Let's thank our speaker one more time.
Thanks.